to be in chapter 2. Hey guys, so we're going to start chapter 2 today, and in this chapter we're going to play chess, chase zombies, watch Mythbusters, and do a lot of problems as usual. I hope that you enjoy it. We got to do some formal notes first. So when we're talking a weight of a graph, we're talking the numbers on the graph. Pens, come on. Do the thing. Do the thing. These numbers on the graph. So these are weights. These weights can be associated with almost anything. They can be associated with money, miles, number of zombies, which you will see in a later example. They are going to help us make decisions about things and how things are related. But first, we need to find the total weight of this graph, and that's where we add up the numbers. So that's just 54 plus 26 plus 72 plus 30 plus 20 plus 98 plus 42 plus 37 plus 68 plus 21. And I'm going to take out my calculator because I can't do math without it. So that gives me a total weight of 468. Now, when we're talking weights of things and trying to find roots of least value or greatest value, we talk about something called Hamilton graphs, Hamilton paths, and Hamilton cycles. A Hamilton path in a graph is a path that includes every vertex exactly once. And then a Hamilton cycle is a cycle that includes every oopsie. Why did you do that to me? Sorry about that. I'm still getting used to the pen tools and the new word. A Hamilton cycle is a cycle that includes every vertex exactly once, except for the start and stop. Okay, because the start and stop is going to be repeated. So if I were to demonstrate that on this graph above, I'm going to make the Hamilton path in green. So I'm just going to go around and hit every vertex. This is not the path of lowest weight. This is not the path of greatest weight. It's just a Hamilton path. We'll get into figuring out how to find those later. And a Hamilton cycle could look something like this, where I hit every vertex exactly once. I'm sorry, my penmanship game is not on point today. So now we are going back to the arrow. Those are just two examples of the Hamilton cycle. Stop it. Hamilton cycles and paths, but we'll go over it some more. But let's look at a helpful way to remember these. I'm going to zoom out a little bit so you can see these pictures. Now here, this picture right here is the triple E virus. So since Euler is every edge, we can say that Euler cycles are the triple E. Hamilton deals with vertices, so Hamilton is vertex. Or it could be the HIV virus, or the HIV. This is a picture of HIV. This is a picture of triple E. These are not ways I expect you to remember them, but it's just a helpful way. Okay. So now we want to determine if each graph has a Hamilton path or an Euler cycle. Now we already know really easily how to find Euler cycles and Euler paths. Here we know we have an Euler cycle. Here we have an Euler path. This has an Euler cycle. I'm just going to start abbreviating. This has an Euler cycle. This has an Euler path. This is not Eulerian. Not Eulerian. Now for Hamilton, we're going to go ahead and trace these. I'm not going to use the highlighter tool. That was crap. But I'm going to indicate Hamilton paths in, probably not blue. Let's indicate Hamilton paths in purple. And a Hamilton cycle in red. Okay? So, Hamilton path. I'm going to start at F. I'm going to go around, and I'm going to stop, but I'm not going to close it off. In order to get a Hamilton cycle here, I can just close this off. Now, this is only one example, but we're just going through some examples right now. So, this guy does not have a Hamilton cycle. This guy can't have a Hamilton cycle. I want you to think about why it doesn't have a Hamilton cycle. But it has something to do with vertex L and the edge adjacent to it. Starts with a B. What is it? Yeah, that's right, bridge. I could hear you saying it. So here's the Hamilton path. I've hit every vertex. Here I have both a Hamilton cycle and a Hamilton path. Ooh, why didn't you stay? Stay. Stay. Here's a Hamilton path here. And I can make this a Hamilton cycle. Here's a Hamilton path here. Does this have a Hamilton cycle? Why not? It's the bridges. So I'm going to start at one bridge. I'm going to go around. I don't even know if I have a Hamilton path here. I don't. I have more than one place where I can start and stop. So, non-Hamilton. Non-Hamiltonian. Same with this one. This one's non-Hamiltonian as well. Okay. I'm going to try and save these pages and email them to you so you have them. Or I'll post them on the Plato site so you can download them. I just need to get back to where we're supposed to be here. Okay, so important things to remember, and you might have figured a few of these out already. The existence of a Hamilton cycle, an Euler cycle, I can speak, tells us nothing about the existence of a Hamilton cycle. There are multiple Hamilton cycles in a graph that has them. Hamilton, I'm going to write paths and cycles. cycles in a graph that has them. Sometimes they'll be unique. Sometimes you have so many you can't even count them. If a graph contains a bridge, then a Hamilton cycle is not possible. A graph can have a Hamilton path. But no Hamilton cycle. Because a bridge, we can have a Hamilton path still. But if we have a bridge, we can't have a Hamilton cycle. What are you doing? Why are you crashing? Don't do this to me. I don't have time for this. Okay. Thank you. If only freaking out at computers worked all the time. If a graph has a Hamilton cycle... Cat? Then it always have a Hamilton path. Okay? So we're going to skip this group work because you need me for this. We'll do this on Monday. What I want you to do is I want you to work on problem set 3. So you're going to find the total weights of the graphs, so both of the graphs. You're going to find the weight of a Hamilton path that begins at A and ends at C. Remember, you have to hit D, E, F, and B in there. For the second graph, find a Hamilton path that begins at E and ends at C. Lots of weights, lots of cycles, and some things that I want you to think about as to why things don't have Hamilton paths and cycles. Then I want you to find the Hamilton cycles in these graphs. Find the Hamilton cycles here or the paths. So for number 8, when I say non-Hamiltonian, I mean they don't have cycles. No Hamilton cycles. Okay? They may contain a Hamilton path. Why are you not? Stay. They may contain a Hamilton path, but I want you to explain why they have no Hamilton cycle. Same with these guys. If it's disconnected, can it have a Hamilton cycle? Think about that. This one, this is totally extra credit. This one's really hard. +5 on your next quiz if you can figure out why it doesn't have one. Some classification questions that you might get stuck on, but I want you to think about them. I think that'll be enough for today. You won't have a quiz on this on Monday. We'll go over it. We'll talk about stuff, and I want to give you formal notes and more. Like, we can combine some things into one quiz instead of having multiple. So I want this for Monday, and I think you guys can do it for Monday, but we'll talk about it. So have a good weekend, homies. Sorry I couldn't be there. I lied. You absolutely need the group work to do the homework. So bear with me. So I'm not going to really go over the group work because I do want you guys to discover the group work. But the whole point of the group work is to show you that when you're looking for Hamilton cycles, or that when you're looking to prove something doesn't have one, is that you have to start with the vertices of degree 2. Okay, if I had a Hamilton cycle, I know that I have to go in and out of each of these vertices. If I go in and out of all of these vertices and they connect, I can't have a Hamilton cycle. I can't draw a straight line either. Okay, so if you see a graph with vertices of degree 2, and those vertices of degree 2 connect, and all other vertices in the graph are ignored, you cannot say you have a Hamilton cycle. What this is something called proof by contradiction. You make an assumption, and then find a contradiction in that assumption. So when I assume that there's a Hamilton cycle, I know that all my vertices of degree 2 have to be there. So that way, I get a contradiction and know that I don't have a Hamilton cycle. I hope that makes sense. All right? Now really have a good weekend.